Hello, and welcome to the Restful Stories. Tonight, we embark on a journey to a world of brilliant light and profound darkness, a place of silent extremes that orbits at the very edge of our sun's fiery breath. We are glad you have joined us for this exploration. And if you enjoy these travels through the cosmos, this is a wonderful moment to subscribe to the channel to be notified of all our future stories. Our destination is a world that has been known since antiquity, a fleeting point of light that dances in our twilight skies. Yet it has remained one of the most mysterious and misunderstood places in our solar system. It is a planet of paradoxes, a tiny, rocky sphere that is heavier than it should be, a sun-scorched desert that hides fields of ice, and an ancient, seemingly dead world that still shows subtle signs of life. For millennia, it was little more than a name, a myth, a challenge for astronomers who could barely glimpse its face. But in the modern era of exploration, we have sent our robotic emissaries on long and difficult voyages to peel back its secrets. What they have found has reshaped our understanding of how planets are born and how they evolve in the most violent and unforgiving of environments. Join us now as we travel inward toward the brilliant heart of our solar system to tell the story of the swift and enigmatic planet, Mercury, in the grand, silent theater of our solar system, where giants of gas and ice drift in the cold dark. Our story begins with the innermost performer, a world of dramatic extremes that hugs the fierce glare of our sun. This is Mercury, and its first and most defining characteristic is its diminutive stature. It holds the title of the smallest planet in our solar system, a distinction it claimed officially only in the early 21st century, after astronomers re-evaluated the status of distant Pluto in 2006. Before that, Mercury was simply the second smallest, a swift but often overlooked neighbor. To truly grasp its scale, one must look to our own celestial companion, the Moon. Mercury is only slightly larger than Earth's moon, and from a great distance, the two could be mistaken for twins, both pockmarked with the scars of ancient impacts, their surfaces a similar shade of charcoal gray. But this familial resemblance is only skin deep, for Mercury is a world unto itself, a planetary entity with a history and a character profoundly different from any satellite. It is a true planet, orbiting the sun in its own right, not bound to a larger world as a mere attendant. Its small size can be deceptive, making it seem almost insignificant. Yet its influence on our understanding of how planets form and evolve is immense. The sheer difference in scale becomes clear when we imagine it beside our home world. You could comfortably fit more than 18 planets the size of Mercury inside of Earth, a mental exercise that reduces the small world to a mere marble next to the globe we inhabit. This comparison of volume paints a vivid picture of a tiny, dense world racing through the inner solar system, an ancient cosmic relic that has endured billions of years of solar radiation and bombardment. To walk its surface would be to traverse a world far smaller than our own. A journey around its equator would cover a distance of about 15,329 kilometers, a trek of roughly 9,525 miles. This is a vast distance by human standards, yet on a planetary scale, it is remarkably contained. It is a journey shorter than the distance from London to Sydney and back again, a circumference that speaks to a world you could circumnavigate in a fraction of the time it would take to travel around the Earth. Like Earth, Mars, and Venus, Mercury is a terrestrial planet, a term scientists use to describe worlds with solid, rocky surfaces. It is a member of the inner circle of planets, a family of dense bodies forged from metal and silicate rock in the fiery youth of the solar system. You could stand on its surface, a dusty, cratered landscape of gray, and feel the solid ground beneath your feet, a stark contrast to the swirling, bottomless atmospheres of gas giants like Jupiter or Saturn. Yet, standing on this small, solid world, you would feel a surprisingly strong pull of gravity for a planet of its size. This hints at a deep secret hidden beneath its crust, a secret that makes Mercury a true planetary enigma. Despite its small frame, it is the second densest planet in the solar system, surpassed only by our own planet, Earth. This is a profound paradox, a cosmic riddle that puzzled astronomers for decades. How can one of the smallest objects be one of the heaviest for its size? What hidden material could be packed so tightly inside this tiny world to give it such extraordinary heft? The answer lies buried deep within its heart, a secret finally confirmed by spacecraft that dared to venture close. Mercury is not what it appears to be. It is not merely a ball of rock. Instead, it is better understood as a colossal ball of iron with a thin, rocky coating. The planet possesses an enormous iron core, a metallic sphere that spans from 3,600 to 3,800 kilometers wide, a diameter of about 2,237 to 2,361 miles. This metallic heart is so vast that it is nearly the size of our moon all by itself, a core that would be a respectable celestial object in its own right. This disproportionately large engine dominates the planet's entire structure and composition, making up a staggering 75% of the planet's total diameter. No other planet in our solar system is so utterly defined by its core. To put this into perspective, we must look again at our own world. The core of Mercury accounts for about 42% of its total volume. Compare that to Earth, whose own formidable iron core makes up only 17% of its volume. Our world is a planet of rock with a metallic center. But Mercury is a planet of metal with a rocky shell. This fundamental difference is the key to understanding everything else about it, from its weak magnetic field to the strange, wrinkled features on its surface. The consequences of this unbalanced anatomy are profound, leading scientists to question the very story of its birth. Perhaps Mercury was once a much larger planet, a world with a thick, rocky mantle like Earth's. One leading theory suggests a cataclysmic impact in the distant past, a collision with a massive protoplanet that stripped away most of its original crust and mantle, leaving behind a wounded world with an exposed, oversized core. The outer shell of Mercury that remains today, the combined layers of its mantle and crust, is incredibly thin, measuring only about 500 to 600 kilometers thick, a sliver of rock no wider than 310 to 373 miles. This delicate crust is merely a veneer, a thin skin stretched taut over the immense, dense core that dictates the planet's past, present, and future. It is a fragile eggshell surrounding a heart of solid iron, a structure that makes Mercury one of the most peculiar and fascinating objects orbiting our Sun. This fragile structure is not a static relic. It is a dynamic and changing world, and the story of its evolution is written directly onto its face. The immense iron core at its center, the very feature that makes it so dense, is also the engine of its transformation. Like a cosmic blacksmith's forge left to cool, this massive metallic heart has been slowly losing its primordial heat over the eons, and as it cools, it contracts. This process of thermal contraction causes the entire planet to shrink. While this planetary shrinkage is imperceptible on a human timescale, its cumulative effect over billions of years has been dramatic, forcing the thin, brittle crust to accommodate a smaller interior. The result is a landscape covered in geological wrinkles, a network of great cliffs and escarpments that crisscross the surface. Scientists call these features lobate scarps, and they are the telltale signs of a world contracting in on itself. These are not gentle folds, but colossal ruptures in the planet's crust, where one section of terrain has been thrust violently up and over another. The scale of these features is staggering. Some of the scarps are more than 1.6 kilometers high, or roughly a mile high, and can run for hundreds of kilometers, or hundreds of miles, snaking across the cratered plains like immense, frozen waves. They are a testament to the immense forces at play within Mercury, a direct and visible consequence of that oversized, cooling core. This evidence of a cooling, shrinking core once led many astronomers to believe that it must have solidified long ago. Yet Mercury held another surprise. Data from the Messenger spacecraft, which orbited the planet in the early 21st century, revealed subtle wobbles in its rotation, tiny variations that could only be explained if the planet's core was not entirely solid. This presented a fascinating contradiction. A core that was clearly cooling and causing the planet to shrink, yet one that remained fluid. There is now compelling evidence that the planet's core is at least partially molten, a sloshing, liquid heart hidden beneath the solid mantle and crust. The solution to this puzzle likely lies in the core's specific chemical makeup. Scientists now believe that Mercury's iron core is not pure, but is mixed with lighter elements, most notably sulfur. This sulfur acts as a kind of planetary antifreeze, significantly lowering the melting point of the iron alloy. This allows the core to remain liquid at temperatures where a pure iron core would have frozen solid billions of years ago. It is this sulfur-rich, molten outer core that generates Mercury's weak magnetic field and allows the planet to maintain a dynamic interior, even as its surface appears ancient and unchanging. This brings us back to the fundamental question of its origin, the reason for its bizarre anatomy. One of the leading theories paints a picture of unimaginable violence in the early solar system. This hypothesis suggests that the Mercury we see today is the battered survivor of a cataclysmic hit-and-run collision. In this scenario, a much larger proto-Mercury, with a more conventional ratio of rock to metal, was struck by a massive planetesimal, perhaps a tenth of its own size. The immense energy of this massive impact would have blasted away a huge portion of the planet's original rocky crust and mantle, flinging it out into space. What was left behind was the dense metallic core and just a thin layer of the original mantle, a planetary wound that never fully healed. A second, competing theory offers a less violent but equally dramatic explanation. It proposes that Mercury formed where it is today, in the searing heat of the nascent solar system. In this early era, the young sun was far more active and hotter than it is now. This theory suggests the intense solar radiation and powerful solar winds were enough to literally vaporize the rock on Mercury's surface. Over millions of years, this process of solar ablation could have boiled away the lighter silicate materials, which were then carried away by the solar wind, leaving behind the heavier, more resilient iron core. Both theories offer compelling explanations for Mercury's strange composition, and the truth may well be a combination of both. Whatever its true history, this peculiar formation has defined its present reality, placing it in an intimate and unforgiving relationship with our star. Mercury is the closest planet to the Sun, a position that dictates the frantic pace of its existence. Its tight orbit means that a year on Mercury, the time it takes to complete one full revolution around the Sun, is a mere 88 Earth days. It lives its life in the fast lane of the solar system, completing more than 4 of its years in the time it takes Earth to complete just 1. To maintain this close embrace with the Sun, it has to move with incredible speed. It has the fastest orbital speed of any planet, traveling at an astonishing 47 kilometers per second, or roughly 29 miles per second. This incredible velocity, a blur of motion through the vacuum of space, is what inspired ancient observers to name it after the swift Roman messenger god. But here lies the planet's greatest temporal paradox. While its year flies by in a flash, its day is an eternity. A single day on Mercury, measured from one sunrise to the next, is 176 Earth days long, a period of time twice as long as its entire year. This extraordinary temporal peculiarity, where Mercury's day is longer than its year, is one of its most counterintuitive and fascinating features. To an observer standing on its surface, the sun would trace a slow, languid path across the black sky, taking an immense amount of time to crawl from one horizon to the other. This creates a bizarre reality where you could celebrate your first birthday on Mercury, having completed a full orbit around the sun, and yet still be waiting for your first full day to even finish. The cause of this strange relationship between day and year is a unique gravitational lock with the sun, a phenomenon known as a spin-orbit resonance. Mercury does not spin freely on its axis like Earth does. Instead, its rotation is tidally influenced by the sun's immense gravity, which has slowed it down over billions of years into a precise and stable rhythm. It rotates on its axis exactly 3 times for every 2 orbits it completes around the sun. This 3-to-2 spin-orbit resonance is a stable, low-energy state that the planet settled into long ago, a delicate dance between its own momentum and the powerful gravitational pull of its star. This is not a simple one-to-one tidal lock like our moon has with Earth, where the same face is perpetually turned towards its parent body. Mercury's lock is more complex, a rhythmic waltz that produces some of the most bizarre celestial phenomena in the solar system. Because of this unique resonance, combined with the planet's highly elliptical orbit, an observer on Mercury would witness a truly surreal spectacle in the sky. The sun would not simply rise and set in a predictable arc. From certain locations on the surface, at specific times in its long day, the sun would appear to rise, climb a short distance into the sky, and then pause, reverse course, and briefly set again below the horizon from which it just came. After this brief retreat, it would then resume its forward motion and rise once more, continuing its slow journey across the sky. This incredible reverse sunrise is a direct consequence of the interplay between the planet's rotation speed and its changing orbital speed. As Mercury approaches its closest point to the Sun, its perihelion, its orbital velocity increases dramatically, briefly becoming faster than its rotational velocity. For a short period, the planet is moving along its orbital path faster than it is turning on its axis. And from the surface, this causes the Sun to appear to move backward in the sky. The same bizarre effect happens in reverse at sunset from other locations, with the sun setting, partially rising again, and then, finally, setting for good. This celestial ballet is a unique feature of Mercury, a visual manifestation of the complex gravitational forces that govern its existence. It is a world where even the passage of the sun cannot be taken for granted. Adding to this orbital complexity is the fact that Mercury has the most eccentric, or least circular, orbit of all the planets. Its path around the sun is a pronounced ellipse, not a gentle, near-perfect circle like Earth's. This means its distance from the sun varies dramatically throughout its 88-day year. At its closest point, perihelion, it is only 46 million kilometers away, or about 29 million miles. But at its farthest point, aphelion, it swings out to a distance of 70 million kilometers, or roughly 43 million miles. This immense variation in distance, a difference of 24 million kilometers, or 14 million miles, has a profound impact on the planet, subjecting it to huge swings in solar radiation and gravitational forces. It is this eccentricity that drives the strange reverse sunrise and also contributes to the extreme temperature differences on its surface. While Earth's seasons are caused by the tilt of its axis, Mercury has a different kind of seasonality, one driven by distance rather than tilt. Indeed, the planet spins almost perfectly upright as it orbits the sun, with an axial tilt of almost zero. This means it does not experience seasons as we know them on Earth. There is no spring, summer, autumn, or winter. Instead, the hot poles of Mercury are the 2 points on its equator that are pointed directly at the sun during perihelion, the planet's closest approach. These regions experience the most intense solar heating, while the polar regions remain in a state of perpetual, frigid twilight. 13 times every century, on average, this unique orbit brings Mercury directly between the Earth and the sun, allowing us to see it as a tiny black dot passing across the brilliant face of our star. This event, known as a transit, is a rare opportunity for astronomers on Earth to study the planet's thin atmosphere and refine their measurements of its orbit, a celestial alignment that reminds us of our place in the intricate clockwork of the solar system. When we turn our gaze from its orbit to its surface, the comparison to our moon becomes unavoidable once again. Mercury's surface is a desolate, ancient landscape, heavily cratered and scarred by billions of years of impacts. It is a museum of solar system history, preserving the record of a violent past. The surface looks remarkably similar to the highlands of Earth's moon, a testament to the fact that both bodies have been geologically quiet for a very long time. It is, in fact, the most cratered planet in the solar system. This is not necessarily because it has been hit more than other planets, but because it lacks the geological and atmospheric processes that erase these cosmic scars. On Earth, impact craters are worn away by wind and water, buried by lava flows, or subducted by plate tectonics. On Mercury, with no significant atmosphere and no active geology to speak of, a crater formed 4 billion years ago can still look almost as fresh as one formed last week. Each crater is a footprint left by a visiting asteroid or comet, a permanent record of a violent encounter in the planet's long and tumultuous history. The stark, unchanging face of Mercury is a direct result of what it lacks. The planet lacks the dynamic and, in many ways, life-giving geological processes that constantly reshape the surface of our own world. There is no evidence of plate tectonics, the grand continental drift that recycles Earth's crust over millions of years. There are no active volcanoes spewing fresh lava to pave over the old terrain, and no significant atmosphere to drive wind and rain. The relentless forces of erosion that wear down mountains and fill in valleys. Without these resurfacing mechanisms, the planet's crust has become a passive canvas, dutifully recording every impact it has sustained since its formation. This cosmic bombardment was most intense during a period known as the Late Heavy Bombardment, some 4 billion years ago. And the evidence of this chaotic era is preserved with pristine clarity. The result is a world saturated with craters of all sizes, from small, bowl-shaped depressions to vast, multi-ringed basins that speak of collisions with colossal asteroids. This ancient, battered surface provides a unique window into the past, allowing scientists to study the population of impactors that roamed the early solar system. One impact, in particular, was so titanic that it nearly shattered the small planet. This event created the largest known impact crater on Mercury, a sprawling feature known as the Caloris Basin. This immense basin is about 1,550 kilometers in diameter, or roughly 960 miles across. A scar so large it could comfortably contain the entire state of Texas. The impact that created Caloris was an event of almost unimaginable violence. An asteroid, likely at least 100 kilometers or 62 miles in diameter, slammed into the young planet, sending seismic waves reverberating through its entire body. The energy released was so immense that it not only formed the vast basin, but also created a bizarre and chaotic landscape on the exact opposite side of the planet. The shockwaves traveled through Mercury's core and converged at its antipode, causing the ground to jumble and fracture into a strange, hilly terrain known as the Weird Terrain. The Caloris Basin itself is a complex structure with a floor filled with smooth volcanic plains, indicating that the impact was followed by a long period of lava flooding from the planet's interior. These smooth plains are younger than the surrounding cratered terrain, and they are marked by their own set of wrinkles and ridges, evidence of the continued cooling and contraction of the planet. The craters that cover Mercury, from the colossal Caloris to the smallest pits, are more than just geological features. They are also a celestial hall of fame. In a tradition established by the International Astronomical Union, the craters on Mercury are named after famous deceased artists, musicians, and authors, a tribute to human creativity on a world of cosmic destruction. This convention has turned the map of Mercury into a cultural landscape, a canvas where science and the arts intersect. Exploring this map, you will find craters named after literary giants like Shakespeare and Tolstoy, composers like Bach and Beethoven, and painters like Rembrandt and Monet. It is a poignant and beautiful tradition, a way of populating this desolate world with the enduring legacy of human imagination. Among the thousands of named craters, one stands out for its whimsical and beloved namesake. A prominent crater, 87 kilometers, or 54 miles in diameter, is officially named Seuss, in honor of Theodore Seuss Geisel, the beloved children's author, better known as Dr. Seuss. This choice, while perhaps surprising, is a fitting tribute to a man whose work sparked the imaginations of millions, a reminder that the spirit of exploration and the joy of discovery are not so different from the creative impulse that drives an artist. When studying these myriad craters, planetary scientists noticed a subtle but significant difference between those on Mercury and those on the Moon. When an object strikes a planet, it ejects a vast amount of material, which then falls back to the surface, creating a distinctive ejecta blanket around the crater. On Mercury, these ejecta blankets are noticeably smaller than those surrounding craters of a similar size on the Moon. This is not because the impacts were less energetic, but because of Mercury's surprisingly strong surface gravity. Being much denser than the Moon, Mercury's gravitational pull is stronger, which means that the material blasted out from an impact does not travel as far before being pulled back down. This results in more compact, concentrated ejecta patterns, a subtle clue that even from a distance hints at the massive iron core lurking beneath the surface. For centuries, Mercury was seen as a barren, sun-scorched wasteland, one of the last places in the solar system one would expect to find water. But the planet of extremes held one of its biggest surprises, hidden in the one place the sun could never reach: the deep, dark floors of its polar craters. Because Mercury's axis has almost no tilt, the craters near its north and south poles are locked in a state of perpetual shadow. The sun's rays, coming in at such a low angle, can never illuminate their floors, leaving them as some of the coldest places in the entire solar system, with temperatures dropping to levels far below what is experienced on the planet's night side. In the 1990s, radio telescopes on Earth detected bright, radar-reflective patches in these shadowed regions, patches that had the distinct signature of water ice. This extraordinary discovery was later confirmed by the Messenger spacecraft, which found direct evidence of vast deposits of frozen water, potentially several meters or several feet thick, sequestered in these permanently shadowed craters. But the story became even more intriguing. It appears this ice may not be pure. The data from Messenger suggested that the ice is often covered by a thin layer of a dark organic material. This dark blanket is thought to act as an insulator, protecting the ice from sublimation into the vacuum of space. The origin of both the water and the organic material is still a subject of debate. They could have been delivered to Mercury by comets and water-rich asteroids over billions of years, the volatile materials finding a permanent cold trap in the polar shadows. As if these discoveries weren't enough to reshape our view of the innermost planet, Messenger's chemical analysis of the surface revealed another profound chemical anomaly. The surface of Mercury is surprisingly rich in sulfur, containing about 20 times more of this element than the surfaces of Earth, the Moon, and Mars. This abundance of sulfur is a crucial clue to the conditions under which Mercury formed, suggesting it was created from building blocks that were much less oxidized than those that formed the other terrestrial planets. While rich in sulfur, the planet's crust is notably poor in other common rock-forming elements like aluminum and calcium, a compositional mystery that scientists are still working to unravel. The most recent and perhaps most startling discovery came from analyzing the darkest patches on Mercury's surface. These low reflectance areas were found to be incredibly rich in carbon, possibly in the form of graphite, the same material found in a pencil lead. It seems the original crust of Mercury may have been a graphite crust, which was later buried by volcanic lavas. This suggests a primordial world with a dark, carbon-rich surface, a stark contrast to the gray, dusty world we see today, adding yet another layer of complexity to the enigmatic story of the Sun's closest companion. The carbon-rich regions and the overall unique chemistry of Mercury's surface, with its sulfur abundance and poverty of aluminum and calcium, are the chemical fingerprints of a complex geological history that continues to unfold even in the relative quiet of the present day. When we look closely at the landscape, specifically in the volcanic plains and impact crater floors, we find other strange features that defy easy explanation. Scientists have discovered peculiar, irregular depressions that look like shallow pits, often with bright material inside them, which they have termed hollows. These hollows are one of the newest and most perplexing geological features to be found on Mercury. They are shallow, rimless, and often merge with one another, giving the impression that the ground is somehow evaporating or collapsing. They are thought to be the result of a process called sublimation, where volatile elements that turn into gas at relatively low temperatures, are escaping from the surface rock and venting into space, leaving behind these characteristic pits. This suggests that even today, the intense solar heat is driving off elements from the minerals in the surface layer. A slow, continuous process of planetary erosion. The presence of these hollows indicates that Mercury's surface material still contains some of these volatile compounds, a finding that contradicts earlier models that predicted all such materials would have been baked off billions of years ago due to its proximity to the Sun. The continued formation of hollows implies that Mercury is, in fact, still geologically active on a small scale, though in a manner entirely unique to this planet. Adding to this evidence of minor, ongoing geological activity are features that suggest ancient but forceful volcanic processes. Scientists have also identified vents on the surface, which appear to be the source of ancient magma-carved valleys, known as sinuous rills, that wind across the landscape. These vents and valleys are relics of a time when Mercury's interior was still hot enough and active enough to push molten rock to the surface. The valleys they created are evidence of enormous, sustained lava flows that reshaped vast areas of the planet before the interior cooled, and the surface froze into its current, heavily cratered state. While the bulk of Mercury's major geological activity, such as global lava flows and massive crustal displacements, occurred billions of years ago, the discovery of the hollows and the continued shrinking of the planet provide new evidence that suggests there might still be some level of minor geological activity today. The planet is not entirely a dead, frozen world. It is a world undergoing a slow, relentless transformation, driven by the physics of its colossal core and its unique chemical composition. This nuanced view challenges the long-held assumption that Mercury, like the Moon, is merely a cold, inert sphere. It is, instead, a world where extreme environmental conditions are driving novel forms of geological change. The environment that drives these processes is, above all, defined by the Sun. Being the innermost planet, Mercury's primary struggle is to maintain any stable atmosphere against the relentless onslaught of solar radiation and solar wind. In truth, Mercury does not possess what we typically think of as an atmosphere. Instead, it has an incredibly thin and tenuous layer of gas surrounding it, which scientists call an exosphere. This exosphere is the thinnest atmosphere of any planet in the solar system, a wispy shroud that is constantly being formed and simultaneously blown away. It is so thin that its atoms rarely collide with one another, behaving more like individual particles zipping around the planet than a coherent gas. The composition of this exosphere has been precisely measured by the orbiting spacecraft. It is made up of a mixture of elements, including oxygen, sodium, hydrogen, helium, and potassium, all of which are very lightweight. These elements are not permanent features. They are transient. The gases in this exosphere are constantly being stripped away by the powerful solar winds, a stream of charged particles pouring out from the sun. However, the exosphere is also constantly being replenished by new particles that are kicked up from the planet's surface rock by micrometeorite impacts, the solar wind itself, and a process called sputtering, where intense solar radiation breaks down surface minerals. This means that Mercury has no real weather to speak of. The concepts of wind, clouds, and precipitation are completely meaningless here. There is no atmospheric pressure, and the planet's surface is directly exposed to the vacuum of space. If you were to stand on its surface, the sky would not appear blue as it does on Earth. Instead, the sky on Mercury would appear completely black, a star-filled void, even in the middle of its long, scorching day. This is because there is no substantial atmosphere to scatter the sun's light, which is the process that makes Earth's sky appear blue. The sun would be a blinding, intense white disk set against the blackness, with stars visible all around it. A bizarre and beautiful view. But it is the temperature, driven by its thin atmosphere and its proximity to the sun, that defines the true nature of this world. Mercury experiences the most extreme temperature fluctuations in the entire solar system. This is a direct consequence of its slow rotation and its lack of a heat-trapping atmosphere. During the 176 Earth days of its rotation, any point on the planet is exposed to brutal heat for an immense period, and then plunges into an equally immense cold for the same duration. The temperature on the sunlit side of Mercury can reach up to 430 degrees Celsius, which is 800 degrees Fahrenheit. This intense heat is enough to melt lead, aluminum, and even some types of rock. Yet, just a short distance away, on the planet's dark side, the temperature can plummet to an astonishing low of negative 180 degrees Celsius, or negative 290 degrees Fahrenheit. The difference between the day side and the night side is a staggering 610 degrees Celsius, or over 1,000 degrees Fahrenheit, making Mercury the undisputed champion of temperature extremes. The highest daytime temperature on Mercury, a scorching heat hot enough to melt lead, presents a fascinating paradox. Despite being the closest planet to the Sun, Mercury is not the hottest planet in our solar system. That title belongs to our other neighbor, Venus, where surface temperatures are even higher and far more uniform, holding steady at a blistering 465 degrees Celsius, or 869 degrees Fahrenheit, day and night. The reason for this difference lies entirely in the nature of their respective atmospheres. Venus is shrouded in a thick, dense blanket of carbon dioxide, an atmosphere so oppressive it creates a runaway greenhouse effect, trapping the sun's heat and turning the entire planet into a furnace. Mercury, on the other hand, with its barely there exosphere, has no such blanket. The intense solar energy that strikes its surface during its long day is quickly radiated back out into space, with nothing to hold the heat in. This is why the night side can become so phenomenally cold. As soon as the sun sets, the stored heat escapes into the vacuum, and the temperature plummets to cryogenic levels. This lack of an insulating atmosphere is the key to understanding the planet's extreme dual nature, a world of both fire and ice, existing simultaneously, just a few hundred kilometers apart. Beyond its thermal and geological peculiarities, Mercury harbors yet another surprise in its deep interior: a global magnetic field. This discovery, first made by the Mariner 10 spacecraft during its flyby in the 1970s, was a profound shock to planetary scientists. At the time, it was widely believed that a planet as small as Mercury, with a core that should have long since cooled and solidified, could not possibly generate a magnetic field. The prevailing theory of magnetic field generation, known as dynamo theory, requires a convecting, liquid metallic core to create the electrical currents that produce a magnetic field. The existence of Mercury's field was the first strong piece of evidence that its core was, against all odds, still at least partially molten. However, the magnetic field it generates is very weak, a mere whisper compared to Earth's powerful magnetic shield. It is only about 1% of the strength of Earth's magnetic field, a feeble bubble of magnetism in the overwhelming torrent of the solar wind. Despite its weakness, it is a true global field with a north and south pole, and it provides crucial insights into the planet's internal structure and dynamics. Further study by the Messenger mission revealed another bizarre characteristic of this magnetic field. It is not centered on the planet's core in a symmetrical way, as Earth's field largely is. Instead, Mercury's magnetic field is significantly offset, with the magnetic equator, the line where the field is perfectly horizontal, shifted far to the north of the planet's geographic equator. This offset is quite dramatic, displaced by about 20% of the planet's radius. This strange configuration suggests that the dynamo generating the field is not operating throughout the entire liquid outer core. One leading hypothesis is that the dynamo is being generated in a relatively thin shell of liquid iron at the top of the outer core, closer to the northern hemisphere. This could explain both the weakness and the peculiar asymmetry of the field, painting a picture of a complex and unique internal engine that is unlike any other in our solar system. The consequences of this weak and offset magnetic field are profound for the planet's surface environment. While it offers some minimal protection, it is not strong enough to stand up to the full force of the solar wind. The solar wind, a constant stream of charged particles flowing from the sun, constantly buffets and deforms Mercury's magnetic field. This interaction creates a dynamic and violent space environment around the planet. The solar wind can twist the magnetic field lines, creating powerful, tornado-like structures that scientists have dubbed magnetic tornadoes. These are not tornadoes in the atmospheric sense, but rather giant, swirling magnetic vortices that connect the planet's magnetic field directly to the interplanetary magnetic field carried by the solar wind. These magnetic tornadoes can be up to 800 kilometers wide, or about 500 miles across, at the surface. They serve as open channels, allowing the hot, energetic particles of the solar plasma to bypass the magnetic shield and rain directly down onto Mercury's surface. This process is a major contributor to the sputtering that replenishes the planet's exosphere as the high-energy particles blast atoms off the surface rocks. It is a dramatic and violent form of space weathering, a direct and continuous bombardment of the surface that is a direct result of the planet's weak magnetic defenses. Beyond the immediate vicinity of the planet, Mercury's interaction with the solar environment produces another, even grander, ethereal feature. The planet has a comet tail, a long, glowing stream of atoms that extends away from the sun, much like the tail of a comet. This tail is not made of dust or ice, but is composed primarily of sodium atoms, which are blasted from the planet's surface by solar wind, sputtering, and micrometeorite impacts. Once these sodium atoms are liberated into the exosphere, the pressure from solar radiation pushes them away from the sun, forming a faint, glowing tail that can stretch for millions of kilometers or millions of miles through space. This beautiful, ghostly appendage is completely invisible to the naked eye, but can be detected with sensitive instruments from Earth. It is a testament to the constant, slow erosion of Mercury's surface, a visible sign of the planet dissolving, atom by atom, into the void. All of these phenomena, the extreme temperatures, the weak magnetic field, the constant bombardment, contribute to a surface environment that is profoundly alien. This environment is also defined by a much weaker gravitational pull than we are used to. The gravity on Mercury's surface is only about 38% of Earth's gravity. This means that if you were able to stand on its surface, you would feel incredibly light. If you weigh 100 pounds on Earth, you would weigh a mere 38 pounds on Mercury, and you would be able to jump nearly 3 times higher than you can on your home planet. This low gravity has also played a role in shaping the planet's geological features, influencing the shape of craters and the height of its great scarps. It is another fundamental characteristic that makes Mercury a truly distinct and fascinating world. That feeling of lightness, the sensation of weighing only 38% of your earthly weight, would be accompanied by a unique and ever-changing view of the heavens. Just as our moon presents a familiar cycle of phases to us, Mercury, being an inner planet, also goes through a full set of phases as seen from Earth. When Mercury is on the far side of the sun from us, we see it in its full phase, a small but fully illuminated disk. As it moves around its orbit, it appears to wane, becoming a gibbous, then a half, and finally a slender crescent. When it passes between the Earth and the Sun, it is in its new phase, its dark side turned towards us, rendering it completely invisible except during those rare transit events. Observing these phases from Earth, however, is a significant challenge for astronomers. Mercury's proximity to the Sun means it is almost always lost in the glare of our star. It is only visible for brief periods, hugging the horizon just before sunrise or just after sunset. This fleeting visibility made it a difficult object of study for early astronomers, a swift and elusive target that demanded patience and skill to observe. Despite this difficulty, Mercury is one of the 5 planets that are visible from Earth with the naked eye, a distinction it shares with Venus, Mars, Jupiter, and Saturn. These 5 worlds, along with the Sun and Moon, were the wanderers of the ancient skies, their movements against the backdrop of fixed stars forming the very basis of astronomy. Indeed, the planet has been known since ancient times, a familiar, if tricky, presence in the sky for countless civilizations. The earliest known records of its observation come from the 14th century before Christ, inscribed on clay tablets by meticulous Assyrian astronomers in Mesopotamia. They knew it as Udu Idim Gu Udulud, the jumping planet, a name that likely reflected its quick, darting movements across the twilight sky. The ancient Babylonians, who inherited much of the Assyrian astronomical tradition, also tracked it with great care, associating it with their god Nabu, the scribe and messenger of the gods. This association with a divine messenger was a common thread that ran through many cultures. The ancient Greeks named it Stilbon, meaning the gleaming, but later came to associate it with their fleet-footed messenger god, Hermes. It was the Romans who ultimately gave the planet the name we use today. They named it Mercury, after their own swift messenger god, Mercury, the Roman equivalent of the Greek Hermes. The name is profoundly appropriate, a perfect encapsulation of the planet's character. Mercury is the fastest orbiting planet in our solar system, racing around the Sun in just 88 days, its celestial speed a fitting tribute to the winged sandals of the god it is named for. Its astronomical symbol, a circle with a cross below and a semicircle above, is a stylized representation of the god's winged helmet and his caduceus, or herald's staff. For millennia, all that was known about Mercury was this single, moving point of light. The invention of the telescope in the early 17th century promised to reveal more. The great Italian astronomer Galileo Galilei and his English contemporary Thomas Harriot were the first to turn their rudimentary telescopes towards Mercury, hoping to resolve it into a disk and perhaps glimpse features on its surface. While their instruments were powerful enough to confirm, that Mercury went through phases like Venus and the Moon. A crucial piece of evidence for the sun-centered model of the solar system. They were not strong enough to reveal any surface details. The planet remained a tiny, blurry, and frustratingly indistinct world. For the next 3 centuries, despite steady improvements in telescope technology, Mercury guarded its secrets well. It was simply too small, too far away, and too close to the Sun for Earth-based observers to make out any reliable surface markings. It was a world that was known to exist, but its true nature remained a complete mystery. It was a blank spot on the map of the solar system. A situation that would not change until the dawn of the space age. Even with the advent of space exploration, Mercury proved to be a difficult target. Its proximity to the Sun and its high orbital speed make it one of the most challenging planets to visit with a robotic probe. A spacecraft launched from Earth must travel not only towards the Sun, but also significantly slow down to be captured by Mercury's weak gravity. This requires an enormous amount of energy and complex orbital maneuvers. Because of these challenges, Mercury has remained the least explored of the 4 terrestrial planets. While Mars has been visited by dozens of orbiters and landers, and Venus has been extensively studied by multiple missions, Mercury has only been visited by 2 dedicated spacecraft in the entire history of space exploration. The first of these pioneers was NASA's Mariner 10. Launched in 1973, Mariner 10 was a marvel of ingenuity, designed to be the first mission to use the gravity of one planet, Venus, to slingshot itself towards another, Mercury. This gravity assist maneuver was crucial for saving fuel and making the mission possible. Mariner 10 did not orbit Mercury. Instead, it made 3 close flybys in 1974 and 1975. During these fleeting encounters, it managed to map about 45% of the planet's surface, providing humanity with its very first close-up look at this mysterious world. The images it sent back were a revelation, unveiling the heavily cratered moon-like surface, the great scarps, and the colossal Caloris Basin. It was Mariner 10 that made the astonishing discovery of the planet's thin atmosphere and its unexpected magnetic field. After its final flyby, Mariner 10 ran out of fuel and is now silently orbiting the Sun, a derelict but historic piece of space hardware. For more than 30 years after Mariner 10, no other spacecraft visited Mercury, and the remaining 55% of its surface remained completely unseen, a modern-day terra incognita. For 3 decades, the images from Mariner 10's partial mapping were all humanity had to go on, a tantalizing but incomplete portrait of the innermost world. The planet remained a place of profound mystery, with more than half of its surface a complete blank. That long drought of information finally ended with the arrival of NASA's Messenger spacecraft, a mission whose name was an acronym for Mercury surface, space environment, geochemistry, and ranging. Launched in 2004, Messenger embarked on a long and winding journey through the inner solar system, a testament to the immense difficulty of reaching its target. It took nearly 7 years and 15 trips around the Sun, including 1 flyby of Earth, 2 of Venus, and 3 of Mercury itself, before it had shed enough orbital energy to be captured by the planet's gravity. Finally, in March of 2011, Messenger achieved what no spacecraft had done before. It successfully entered into orbit around Mercury. This historic achievement marked the beginning of a new era of exploration for the Sun's closest companion. Over the next 4 years, Messenger orbited the planet from a low altitude, its sophisticated suite of instruments meticulously studying every aspect of the world below. It was a mission of profound discovery, one that would completely rewrite our understanding of this enigmatic planet. From its vantage point in orbit, Messenger systematically mapped the entire globe, finally filling in the vast, uncharted territory left behind by Mariner 10. For the first time, the entire surface of Mercury was revealed to us, a complete and detailed global map that unveiled a world far more complex and varied than previously imagined. The spacecraft's high-resolution cameras captured stunning images of the surface, revealing the hollows, the volcanic vents, and the full extent of the Great Scarps. Its spectrometers analyzed the chemical composition of the crust, discovering the unexpected abundances of sulfur and carbon, and the surprising poverty of aluminum and calcium. Its laser altimeter precisely measured the planet's topography, confirming the existence of water ice in the permanently shadowed polar craters, and helping to prove that the planet's core was at least partially liquid. Messenger's data transformed Mercury from a poorly understood point of light into a complex and dynamic world with a rich and violent history. After far exceeding its original mission plan, the spacecraft ran out of fuel in April of 2015. In a final, dramatic act, it was deliberately crashed into the planet's surface, creating a new, small crater that will one day bear its name. Messenger's legacy is a treasure trove of data that scientists will be analyzing for decades to come, a comprehensive biography of a world that was once almost a complete unknown. Even now, the exploration of Mercury is not over. A new chapter is currently unfolding as a joint European and Japanese mission, named Bepi Colombo, is making its own long journey to the innermost planet. Launched in 2018, Bepi Colombo is an ambitious and complex mission, consisting of 2 separate orbiters traveling together. One, built by the European Space Agency, is designed to study the planet itself, while the other, built by the Japan Aerospace Exploration Agency, will focus on studying its magnetosphere. This dual approach will provide an unprecedentedly detailed look at the planet and its interaction with the solar wind. Like Messenger, before it, Bepi Colombo is taking a long and circuitous route, using multiple gravity assists from Earth, Venus, and Mercury itself to gradually lower its orbit. It is expected to finally arrive and enter orbit around Mercury in December of 2025. When it does, it will begin a new phase of discovery, building on the foundation laid by Messenger and promising to answer many of the lingering questions about this strange and fascinating world. The very fact that such complex, long-duration missions are necessary underscores the immense challenge of visiting Mercury. It is a journey that seems counterintuitive. One might think that traveling to a planet closer to the Sun would be easier than traveling to one farther away, but the opposite is true. The Sun's immense gravitational pull dominates the inner solar system. A spacecraft launched from Earth is already traveling at a high speed in its orbit around the Sun. To get to Mercury, it must essentially fall inward towards the Sun, but it must do so in a controlled way, shedding a huge amount of its orbital velocity to allow it to be captured by Mercury's much weaker gravity. This requires a massive amount of propellant for braking maneuvers, or the use of these clever, time-consuming gravity assists to slow down. It is a far more energy-intensive journey than traveling outwards to Mars, a reality of orbital mechanics that has kept Mercury one of the most exclusive destinations in the solar system. This exclusive world holds a place of solitary distinction. When we look at the other planets, we see a rich tapestry of moons and rings. Earth has its one large moon. Mars has its two small captured asteroids, and the gas giants boast vast and complex systems of dozens of satellites and spectacular rings. Mercury, however, stands alone. It has no moons. It also has no rings. It is a world stripped bare of any adornment, a single, solitary object in its swift orbit around the Sun. The reasons for this cosmic loneliness are tied directly to its defining characteristics: its small size, its weak gravity, and, most importantly, its proximity to the Sun. Any moon that might have formed around Mercury in the early solar system, or any that might have been captured by its gravity, would have been in a highly unstable orbit. The immense gravitational influence of the nearby Sun would have quickly perturbed such an orbit, either flinging the moon out into space, or more likely, causing it to crash into Mercury or the Sun itself. The same gravitational forces would prevent the formation of a stable ring system, which requires a gentle and undisturbed environment to persist. Mercury is simply too close to the overwhelming bully of the solar system to hold on to any companions of its own. From the surface of this lonely planet, that bully, our Sun, would be a terrifying and magnificent sight. It would appear more than 3 times larger in the sky from Mercury than it does from Earth. This is a simple consequence of its close proximity, a view that would change dramatically throughout Mercury's eccentric orbit, with the Sun appearing largest at perihelion and smallest at aphelion. the intensity of the light would be equally overwhelming. The sunlight on Mercury's surface would be as much as 7 times brighter than it is on a clear day on Earth. It would be a truly blinding glare, a torrent of radiation that has shaped every aspect of the planet's existence, from its geology to its non-existent weather. Given its long and distinguished history as an object of human observation, stretching back to the dawn of astronomy, it is impossible to say who officially discovered Mercury. Unlike planets like Uranus and Neptune, which were discovered at specific moments in history by specific individuals using telescopes, Mercury has always been with us. It is a part of our shared human heritage, a wandering star that has captivated the imagination of sky-gazers for thousands of years. It was not discovered, it was simply known, a fundamental piece of the celestial furniture, its true nature only being unveiled in our own time. This ancient and familiar celestial object, a fixture in the human sky since antiquity, played a pivotal and somewhat unexpected role in one of the greatest scientific revolutions in history. For centuries, astronomers had meticulously tracked the movements of the planets, using the powerful mathematical framework of Isaac Newton's laws of motion and universal gravitation. Newton's laws were spectacularly successful, predicting the orbits of the known planets with astonishing precision. But there was one nagging exception, one small but persistent anomaly that defied all explanation: the orbit of Mercury. Astronomers in the mid-19th century, most notably the French astronomer Urbain Le Verrier, had discovered that Mercury's orbit was not perfectly stable. The entire elliptical path of its orbit was slowly rotating around the Sun, a phenomenon known as perihelion precession. The perihelion, the point of closest approach to the Sun, was gradually shifting its position in space with each successive orbit. While a small amount of this precession was expected and could be explained by the gravitational tugs of the other planets, particularly Venus and Jupiter, there was a tiny discrepancy. After all the known gravitational influences were accounted for, Mercury's orbit was still precessing by a minuscule but undeniable 43 arc-seconds per century. An arc-second is a tiny unit of angular measurement, 1/3600th of a degree, so the discrepancy was incredibly small, but it was real, and it was a direct challenge to the perfection of Newtonian physics. Le Verrier and others were convinced that there must be an undiscovered planet orbiting even closer to the Sun than Mercury, a small, hidden world they named Vulcan. They believed that the gravitational pull of this hypothetical planet was what was causing the extra precession in Mercury's orbit. For decades, astronomers searched for Vulcan, especially during solar eclipses, but it was never found. The mystery of Mercury's wobbling orbit remained one of the great unsolved problems of celestial mechanics. The solution, when it came, was not a new planet, but a new understanding of gravity itself. In 1915, a young German physicist named Albert Einstein published his theory of general relativity. This new theory described gravity not as a force acting at a distance, as Newton had, but as a curvature in the fabric of space-time caused by the presence of mass and energy. According to Einstein, massive objects like the Sun warp the space-time around them, and planets like Mercury are simply following the straightest possible path through this curved space-time. When Einstein applied the complex equations of his new theory to the orbit of Mercury, he found that it predicted an extra amount of precession, an effect that would be most pronounced for a planet moving so quickly and so close to a massive star. The value he calculated perfectly matched the unexplained 43 arc seconds per century. It was a stunning confirmation of his theory, and the first strong piece of observational evidence for general relativity. Mercury's orbital wobble was no longer an anomaly. It was the first proof of a new and more accurate description of the universe. This world, so instrumental in confirming a new theory of physics, is also a world that challenges our ideas about the conditions necessary for life. Given its extreme temperatures, its lack of a substantial atmosphere, and its intense radiation environment, it is not surprising that Mercury is considered a highly unlikely place to find life as we know it. The surface is sterilized by a combination of brutal solar radiation and the constant influx of energetic particles from the solar wind. Any complex organic molecules on the sunlit surface would be quickly broken down, while the discovery of water ice and organic materials in the permanently shadowed polar craters has sparked some speculation about the possibility of prebiotic chemistry in these unique, protected environments. The overall conditions on the planet remain profoundly hostile. The planet's very formation and composition also tell a story of a world forged in conditions far from the gentle cradle of Earth. The materials that originally came together to form Mercury may have been sourced from a wide region of the inner solar system, not just from the area immediately adjacent to its current orbit. This idea, supported by chemical analysis of its surface, suggests that the early solar system was a much more chaotic place, with planet-building materials being scattered and mixed over vast distances before finally accreting into the planets we see today. Mercury's unique, iron-rich composition might be the result of it forming from a particularly metal-rich collection of these early building blocks. Like the other terrestrial planets, including our own, it is almost certain that Mercury had a magma ocean early in its history, a period when its entire outer layer was a sea of molten rock. This is a common phase in the formation of rocky planets, a result of the immense heat generated by the accretion of smaller bodies and the decay of radioactive elements. This global magma ocean would have eventually cooled and solidified from the bottom up. a process that would have led to the chemical differentiation of the planet, with heavier elements like iron sinking to form the core and lighter silicate minerals rising to form the mantle and crust. The unique properties of Mercury's crust today are a direct legacy of this early molten phase. The planet's composition is now estimated to be approximately 70% metallic and a mere 30% silicate material, a ratio that is completely inverted compared to Earth, which is mostly silicate rock with a smaller metallic core. This dramatic difference in composition is the planet's most defining feature, the source of its high density, and the root cause of its peculiar geology. The structure of the planet that resulted from this formation process is one of distinct and dramatic layers. The crust, the outermost layer, is believed to be between 100 and 200 kilometers thick, or roughly 60 to 120 miles thick. This is significantly thicker than Earth's continental or oceanic crust, but it is still just a thin skin covering the vast layers beneath. Below this rocky crust lies the silicate mantle, a layer surrounding the core that is about 600 kilometers thick, or approximately 370 miles. While substantial, this mantle is incredibly thin relative to the size of the core it encloses. Another consequence of whatever ancient process stripped Mercury of its original rocky material. And at the center of it all is the colossal iron core, the dominant feature of the planet, a metallic heart that makes up the vast majority of its mass. This core is itself likely layered, with scientists believing that the iron in Mercury's core probably contains other elements, such as nickel and silicon, mixed in, which would affect its density and its thermal properties. This intricate internal structure gives rise to a surface gravity that is surprisingly strong for such a small world. In fact, Mercury's surface gravity is slightly higher than that of Mars, even though Mars is a significantly larger planet with more mass. This is a direct testament to Mercury's incredible density. Its material is packed so tightly that its gravitational pull is stronger than that of its larger but less dense planetary neighbor. The chemical story written on Mercury's surface provides our deepest insights into the conditions of its birth. Beyond the high concentrations of sulfur and carbon, Messenger's instruments detected another compositional quirk, a high ratio of magnesium to silicon on its surface. This specific chemical signature, when compared to the compositions of other terrestrial planets and various types of meteorites, serves as a powerful fingerprint for the raw materials from which Mercury was built. The particular blend of elements suggests that the planetesimals that accreted to form Mercury were chemically distinct from those that formed Earth, Venus, or Mars. This evidence further supports the idea that the inner solar system was not a smooth gradient of materials, but a messy and heterogeneous environment where different types of planetary building blocks were available in different locations. Complementing this observation is the discovery of remarkably low surface abundances of both titanium and iron in the silicate crust. This is particularly puzzling because iron is the planet's single most abundant element overall. Yet very little of it appears to be chemically bound in the rocks of its crust and mantle. This suggests that the process of differentiation on Mercury was incredibly efficient, with the vast majority of the heavy iron sinking to the core, leaving behind a mantle and crust that were unusually depleted in this element. Taken together, these chemical clues, the high sulfur, the high magnesium to silicon ratio, and the low iron in the crust, all point towards a single, compelling conclusion. Mercury likely formed in conditions where oxygen was much more scarce than it was in the regions where Earth, Mars, or Venus formed. In scientific terms, it formed in a highly reduced chemical environment. In an oxygen-rich environment, iron readily combines with oxygen and silicon to form dense, iron-rich silicate rocks, which would have been incorporated into the mantle. The fact that this did not happen on Mercury, and that so much of the iron remained in its metallic form to create the massive core, strongly indicates a lack of available oxygen during its formation. This idea has become a cornerstone of modern theories about Mercury's origin, helping to explain its anomalous density and unique composition. The visual manifestation of this unique world is a landscape dominated by craters. But even these are not all the same. Some of the younger, more pristine craters are surrounded by brilliant, ray-like systems that stretch across the dark surface for hundreds or even thousands of kilometers. These bright ray systems are formed by the pulverized material that was violently ejected during the impact event. This fine, bright dust blankets the older, darker terrain, creating spectacular starburst patterns that are among the most striking features on the planet. They are the signatures of the most recent large-scale impacts, cosmic graffiti, that will remain visible for hundreds of millions of years until the slow process of space weathering gradually darkens them to match their surroundings. Our understanding of Mercury's interior has also become more refined, moving beyond a simple model of a core and mantle. The current, most sophisticated model suggests a complex, multi-layered core. At the very center lies a solid inner core, much like Earth's, which is surrounded by a larger, liquid outer core. It is the convective motion within this liquid outer core that is thought to generate the planet's magnetic field. But uniquely, scientists now believe there may be another layer on top of this, a solid shell of iron sulfide that precipitated out of the liquid core as it cooled. This layered internal structure, a solid inner core, a liquid middle core, and a solid outer core shell, all wrapped in a thin silicate mantle and crust, is a far more intricate picture than we had just a few decades ago, and it helps to explain some of the planet's more puzzling gravitational and magnetic field data. From our distant vantage point on Earth, the planet itself appears as a tiny, bright point of light. Astronomers quantify this brightness using a scale called absolute magnitude, and Mercury has an absolute magnitude of negative 0.4. This makes it one of the brighter objects in our night sky, though its proximity to the sun often makes it difficult to see. Its apparent size in our sky also varies dramatically due to its eccentric orbit. The angular diameter of Mercury, as seen from Earth, ranges from a tiny 4.5 arcseconds when it is at its farthest point from us, to a more substantial 13 arcseconds when it is at its closest approach. For comparison, the full moon has an angular diameter of about 1,800 arcseconds, underscoring just how small and distant Mercury appears, even at its best. We have also refined our measurements of its rotation. While we know its solar day, from sunrise to sunrise, is about 176 Earth days, its sidereal day, the time it takes to rotate once with respect to the distant stars, is a much shorter 58.65 Earth days. It is the combination of this 58.65-day rotation and its 88-day orbit that results in the long solar day, a perfect illustration of the complex celestial mechanics of its 3-2 spin-orbit resonance. Finally, our knowledge of its tenuous exosphere has grown to include trace amounts of other gases beyond the main components. Scientists have detected fleeting hints of argon, carbon dioxide, water vapor, and even heavier noble gases like xenon and krypton. These are likely released from the planet's interior through outgassing or delivered by cometary impacts, but they are quickly lost to space, transient whispers in an almost perfect vacuum. This brings us to a final, mind-bending consequence of Mercury's strange temporal dance. Because of its unique 3-2 spin-orbit resonance, a specific spot on Mercury's equator will experience a period of continuous, searing sunlight for one full Mercurian year, or 88 Earth days. This is followed by an equally long period of profound cryogenic darkness, a full Mercurian year spent on the night side of the planet. It is a world of incredible extremes, where the rhythm of life, if it could exist, would be dictated by a calendar in which a single day lasts for 2 full years. A final, fitting paradox for the most enigmatic of the terrestrial planets. And so, our journey concludes. We retreat from its sun-blasted surface, leaving behind the silent, shadowed craters and the vast, wrinkled plains. We have traveled from its colossal iron heart to the wispy, glowing atoms of its comet-like tail, and in doing so, have pieced together the story of a world that defies simple categorization. It is a planet forged in fire, yet cradling reservoirs of ancient ice, a world of incredible speed, yet of impossibly slow days. It is the ultimate survivor of a chaotic past, a world perhaps stripped down to its very core, yet one that still possesses the energy to generate a magnetic field and the grace to paint the sky with its ghostly sodium tail. For centuries, it was a challenge, a riddle in the sky, whose strange dance helped us to reimagine the very fabric of the universe. Now, it is a destination. The data from our robotic explorers has transformed it from a myth into a place of complex geology and exotic chemistry, a natural laboratory for the most extreme of planetary processes. The next time you cast your gaze toward the fading glow of sunset or the first light of dawn, and you see that single, bright point of light hugging the horizon, you will know the profound story it holds. It is no longer just a wandering star, but a world unveiled, a testament to our relentless curiosity, and a permanent, shimmering jewel in the crown of our sun.